Yes, sir.
Good. Um, so we have finished our chapter 3, and then our next step, chapter 4, is called applications of derivatives. We have studied um, limits, continuity, and differentiation. Especially, we spend a lot of time on differentiating functions with various different techniques. So, our next chapter is about applications of derivatives. Why are these derivatives important? Um, okay, give me a second. I'm still having trouble to log into the system. By the way, do you have any questions about last sections? Do you have anything in particular that I need to discuss again? Somebody says we did not finish 3.7 and 3.8. Um, those are for you to read and study by yourself. Those are just applications of derivatives in physics and biology. So you should go there and read those by yourself, understand those. If you need, I can go through them quickly, but I'm not planning to spend much time on those topics. Huh? Okay. Okay. Now you should see uh, these notes on extreme notes called extreme values of continuous functions. Um, so one of the very important things that we notice about different derivatives is at this when the function reach to a maximum or a minimum point, the tangent line become horizontal. That means derivative is zero. So to find these maximum and minimum points, we need to have zero derivative. We need to look at zeros of the derivative. So that is the focus of this section, how to find maximum and minimum points. So we are going to discuss them in details. We are going to have a systematic discussion on those maximum and minimum points. Okay, so These maximum and minimum points are called extreme values. So let's talk about extreme values of a continuous function. Graph with an unbroken a function with an unbroken graph. Um, there are two types of extreme values. Few different types of extreme values. Those can be categorized into two different things called maximum points and minimum points. And there are two different types of absolute maximas and minimas as well. Absolute maximum is the highest, like the largest maximum. At an absolute value, absolute maximum, f of x bigger than or f of c bigger than or equals f of x for all other x values in the domain. So that means at this point c, function reached to a maximum, and that maximum is bigger than any other point in the domain, any other function value. Likewise, absolute minimum means, yeah, you have reached to a smallest value. Minimum, and that minimum value is smaller than any other function value. So you can see those from this graph. So this is like a part of a parabola. At point 2 comma 5, your function has reached to a maximum point, and that maximum point is bigger than any other function value. And point 0 comma 1, function reached to a minimum point, and that minimum is the smallest function value. And if you look at this other endpoint, minus 1 comma 2, that is also a sort of a maximum point. If you think about a small region around this point, think about a small region around the graph. This is sort of a maximum, but not the absolute maximum. Those kind of maximum points are called local maximums. Locally, those looks like uh, maximum points. Imagine a mountain range, and there are peaks in this mountain range, and there will be a tallest mountain in the range. That is the absolute maximum. And any other peak will be a local maximum. Any other smaller mountain will be top of any other smaller mountain will be a local maximum, not the absolute maximum. Absolute, there is only one absolute maximum, that is this tallest mountain. Now, in this graph, we can see the domain of the function is from -1 to 2, -1 to 2. Those are the possible input values, possible x values. If you think about possible outputs, they range from 1 to 5. Those are the possible y values, possible outputs. So domain is from -1 to 2, range is from 2 to 5. Now, in this case, both endpoints of the domain are also included, -1 and 2. So it is closed interval, -1 to 2, closed interval. Now let's think about the -1 to 2 open interval. In that case, we still have a very similar graph, but there is a very significant difference too. Now we don't have these endpoints. Those endpoints are false, because 2 is no longer in the domain. Any number below 2 will be in the domain. So you can think about 2.5, 2.6, 2, sorry, um, 1.5, 1.9, 1.99, 1.999. All these numbers are in the domain, but not 2. You can reach to 2 from the left hand side, any other intermediate, but not 2. So you could compute the limit of this function as you approach to 2 from the left hand side. Uh, Likewise, again at -1, we have the same problem. -1 is not in the domain. Because of this, because of the absence of these endpoints, um, you no longer have this absolute maximum point. We don't have this absolute maximum point. And also, we don't have this local maximum at -1. This function has no maximums, no absolute maximas, no local maximas. Uh, However, it still have this absolute minimum point. So there is a very significant difference when you even remove by removing a single point, you can change the picture completely. Now, if you think about changing the domain to something like closed at -1, then open at 0, union, open at 0, and then again closed at 2. That means you take the closed interval from -1 to 2 and remove 0. In that case, you have absolute maximum, local maximum, but you don't have absolute maxima, minimas, and these local minimas and local maximas. You cannot have missing points in the domain. You have to have something like this. You have to have a closed interval. We cannot have these missing endpoints or missing middle points. You have to have a closed interval, closed complete interval with no missing points. This is called the extreme value theorem. If f is a continuous function on a closed interval, then f has both absolute maxima and absolute minima. Extreme value theorem guarantees us the existence of these absolute maximas and absolute minimas if the domain is a closed interval like a comma b. Um, so then that's about absolute maximas and absolute minimas. Relative maximas means the another name for local maximas and local minimas. Relative means they are sort of maximums, but they may not be the largest maximum, like these peaks of smaller mountains. So if it has a relative maxima at C, then f of C is bigger than f of x for an small interval containing point C. So if it is locally maximum. Think about this smaller mountain uh, for a region around the mountain. This smaller mountain, top of the smaller mountain is the highest point. So locally it is a maximum, but in the large scale it is not. It may not be the maximum. Same thing is true for relative minima. Now instead of a mountain, you can think about a valley. F has a relative minimum at C if f of c is smaller or equal f of x for all x values in an open interval containing point C. Let me draw a picture for you. This point is according to the picture, this is the absolute maximum. Mm, This is the absolute minimum. By the way, I'm also including these endpoints too. Then right over here, I have a local maximum. If you think about a small region on the graph, this is a maximum. So this is a relative um, maximum. This point is a relative minimum. Now all together these maximum and minimums are called extreme values. Now, if we go back and think about derivatives, we know at some points derivative is zero, and at those points, that means horizontal derivative, horizontal tangent lines. Example, right over here, derivative is horizontal. So tangent line is horizontal, therefore we have a zero derivative. Again, right over here, tangent line is horizontal. But at this point, tangent line doesn't seem like a horizontal line. Again, over here, we have a problem. So we have the same problem. So at some horizontal, some of these maximum or minimum points, we have horizontal tangent lines. At some point, we don't have those. So we cannot say at every maximum point we have a horizontal tangent line. At some points we have horizontal tangent lines, at some points we don't. So we have to distinguish them, we have to separate them. We call a critical point if either derivative is zero or derivative does not exist. Hmm? So derivative equals zero or derivative does not exist. That's kind of important because at some of the maximum or minimum points, we may not have derivative at all. Hmm? Let me give you an example. Think about the graph of absolute value of x. Um, Absolute value means you take the number without considering its sign. You change all the minus signs to plus signs. The graph looks like this wedge shape, V shape, and it has a smallest value, or a minimum value, absolute minimum at origin, but at the same point we have a problem. Problem regards to the derivative. For every positive value, derivative is 1. For every negative value, derivative is minus 1. But at 0, as we approach to 0 from the right hand side, derivative seems plus 1. As we approach to 0 from the negative side, means from the left hand side, derivative seems minus 1. They don't agree. At x equals 0, derivative does not exist. So, but still it is an absolute maximum, absolute minimum. So, derivative 0 or derivative does not exist can be important. So, critical points means equals 0. Or it does not exist. If one of these happens, we say that is a critical point. For example, for the absolute value function, we have a critical point. This is a critical point. And for this picture, we have two critical points here and here. Those are critical points, and those are the only critical points for that graph. So critical points. Using the derivative, we can compute, we can find critical points. Critical points are, the definition of critical points are all about derivatives. It is not about maximas or minimas, it is about the derivative. It looks at the derivative and see whether it is zero or whether it is undefined. If it is so, we say it is a critical point. For example, for the absolute value function, every non-zero point is not an absolute value because if that point is positive, derivative exists and it is plus 1. For a negative value, again it exists and value is minus 1. So all the positive and negative values are not critical. Only the zero. Zero at zero, derivative does not exist, therefore it is uh, a critical point. Let me give you a piecewise function. Now the graph of this function looks like until plus 2 uh, function is linear from all the negative values and all the positive values up to plus 2 it is a line with slope 1 and y-intercept equals y-intercept equals plus 1. So looks something like this. Then at 2 both function values agree and 2 it is 3. And after 2 function is constant. Now if you compute the derivative of this function until 2 slope is 1. But we at 2 we have a problem because as you reach to 2 from the left hand side slope is 1. As you reach to 2 from the right hand side graph is horizontal. So derivative is 0. The derivative is 0 if x bigger than 2. And this must be 2. So we have a problem at 2. At 2, derivative is undefined. So derivative does not exist. And after 2, derivative is 0. So if you think about critical points includes 2 and every other value bigger than 2. So set of critical points looks like 2 to infinity, including 2. These are the critical points. These are the critical points. So sometimes these critical points are isolated, like for the graph of absolute value. Or like here, critical points are isolated points. But sometimes they can form an intervals like this, not isolated. Mm, Critical points are where we have pseudo derivatives or undefined derivatives. Um, The x coordinate at a critical point is called a critical number. Critical number theorem is, so critical points are about derivatives. So we first had this discussion about absolute maximums and absolute minimums. Then the extreme value theorem said if the domain is a bounded closed interval derivative, if the domain is bounded closed, then absolute maximums and absolute minimums exist. Hmm? It simply said those exist. Hmm? But one of the deficiencies of this absolute value theorem is it just says both absolute maximum and absolute minimum exist, but it does tells us how to find those. It doesn't tells us how we can find the extreme values. The critical number theorem says you can find those if you look at critical points. If you look at zeros of the derivative or undefined points of the derivatives, those are either relative maximas or relative minimas for the function. Critical number theorem tells us that those absolute extrema can only occur critical numbers or undefined points of the derivative. Hmm? And also, you need to look at endpoints of the domain because uh, if I go all the way back to mm, these endpoints, if I go all the way back to this top picture, over here, derivative, if you think about it actually, we only have, uh, we don't actually have the derivative at that point. We only have this, at this point, we only have the right limit of the derivative. Hmm? Right limit of the derivative exists, but not the full derivative because left limit of the derivative does not exist as there is no way we can approach this point from the left hand side. Hmm? So at this particular point, derivative does not exist. Hmm? Derivative does not exist. Again, for the same reason, because there is no way we can draw, we can find the total derivative. We can find the left derivative, or rather left limit of the derivative. Hmm? So here is the full picture. I'll combine those extreme point theorem and critical point theorem and gives you as a single statement. The first point is if the domain is the bounded closed interval. A comma B Then to find, I'll combine those. I'll talk about maximas and minimas in general. Maximum and minimum points of the function f, we must look at three things. First of all, zeros of the derivative. Second point, undefined points of the derivative. These undefined points in particular includes uh, endpoints of the domain. So endpoints of the domain are actually included in these points. Because if the domain is something like AB, the graph of this function looks um, it may look something like this. So critical points are here, 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 and here. These middle critical points are zeros of the derivative, and these endpoints are undefined points of the derivative. At those points, we have the function, but we don't have a well-defined derivative. We can talk about left and right limits of the derivative, but that doesn't mean it is the derivative. So these critical points. Let's talk about minimum points. So minimum points may look like this. Hmm? Or they may look something like this. Hmm? This is a minimum point. At this minimum point, derivative does not exist. It is not. At this minimum point, it is zero. So these undefined points are also quite important. So you can draw similar pictures for um, maximum points. Okay. So max or minimum essentially implies you need to look at critical points. This implication doesn't go the other way. Okay. Um, if you have a maximum, if you are looking for a maximum and minimum points, you should always look at critical points because every maximum or minimum point is a critical point. It doesn't go the other way. Some of the critical points are not maximums, no minimum points. Let me give you an example. Uh, let's think about it. Y equal x cubed. The derivative is 3x square. So derivative equals 0 means 0. So 0 comma 0 is a critical point. Now when you look at the graph of this cubic function, it looks something like this. At 0 you have a horizontal tangent line, then it goes like that. Before the critical point, derivative is positive. And right over the critical point, derivative equals 0. And after the critical point, derivative is again positive. So this is a point where you have a horizontal tangent line, but at the same time, it is not a maximum nor a minimum. These are called inflection points. Hmm? Critical point, but not maximum or minimum points. These are kind of rare, but they do exist. So every maximum and minimum point is a critical point. Critical means either derivative is zero or undefined. And some critical points are not maximums nor minimums. In either case, critical points are important, zeros of the derivative are important. You need to consider them and see whether these critical points are maximums or minimums, or they may be inflection points like this. So if you want to go back and say, they may be maximum points or minimum points or inflection, right? All right, let's go back to our notes. So to find those, let's look at some examples. Um, Find the critical numbers. Critical numbers means see those x coordinates of critical points. Suppose the derivative is, let's say we are given the derivative, not the function. If the derivative is 1 minus 2 cosine x, then to find the critical points, we look at zeros of the derivative. Points where we have zero for the derivative. If the derivative is 0, cosine x is 1 half, then you draw the unit circle and see where you have cosine x equals 1 half. Um, Hmm. You're given the derivative 1 minus 2 cosine x. If you want, you can think about the function. What function gives you this derivative? Uh, if the derivative is 1, to have 1 as the derivative, we must have x. Hmm? And minus 2 is a constant in front. So in the function also it must be like this. Then cosine x. Derivative of sine is cosine. All right, this should be sine x. So that must be our function. So we are trying to find the maximum and minimum values of this function on the domain 0 2 pi. Okay, domain is a bounded closed interval. Therefore, it must have extreme points. It must have extreme values. Now, let's find critical points. This derivative is well defined everywhere. It doesn't have any undefined points. To have undefined points, it must have like divided by zero or uh, negative value of square root, something like that. Square root of a negative. We don't have anything like that here. So if you say derivative equals zero, you get cosine x equals 1/2. We need to find all these x values for which cosine x equals 1/2. Uh-huh. It's true by unit circle. And we know one value, x equals one value with this property, one x value. Sine 60, sine 6, so the cosine 60 is 1/2. 60 means pi by 3. Remember, cosine is adjacent divided by hypotenuse. Adjacent is the x coordinate. This way is 1/2, this height is 1, this is pi by 3. If you think about all the other values, to have the same x coordinate, we can think about this angle in the fourth quadrant. That angle in the fourth quadrant has the same x coordinate. Since this is pi by 3, this must be pi by 3. So we need this whole thing. 2 pi minus pi by 3. So pi by 3, comma, 5 pi by 3. Those are the only two angles that has this positive 1/2 as the corresponding x coordinate. So these are the only two critical points. Mm, Now, if you want, let's look at the domain of this function. Domain is 0, 2 pi. Somewhere over here we have pi by 3. Somewhere here we have pi by 3. Let's see how the function behaves. function is x minus sine, so 2 sine x. At 0, f of 0 is 0. F of pi by 3. Let's compute that. That's pi by 3 minus 2 sine pi by 3. Sine 60 square root 3 divided by 2. So this is pi by 3 minus square root 3. And let's compute f of pi by 3. Again, this is pi by minus 2. Let's see. Over here, sine cosine pi by 3, y coordinate is square root 3 divided by 2, right? And for this pi by 3, it must have the same y value but with a minus sign. So times minus, because remember, sine of some angle is the y value corresponding y value on the circle. So this is pi by 3 plus square root 3. At 2 pi, f of 2 pi is 2 pi minus 2 times sine 2 pi. 2 pi means like we are at this point of the circle. At that point, y coordinate is 0. So it's just 2 pi. So we computed the y coordinate at every point. Why not y coordinate? The function value. Uh, Let me take the same 4 points and see whether I can identify the nature of these critical points. Um, so for that, I'll try to identify whether these points are minimums or maximums. Uh, Let me think about the derivative. When it comes to derivative, all that matters is the sign of the derivative. Because sign of the derivative tells me whether the function is increasing or decreasing. The derivative is 1 minus 2 cosine x. On the unit circle, for angle theta, cosine theta is the x coordinate. For the unit circle, when theta is 0, x coordinate is 1. And on top of this, cosine theta is 0, because the corresponding x coordinate is 0. Right over here is minus 1. Again, at the bottom of the circle, it is 0. What happened is from theta equals 0 to 90 degrees, cosine theta is decreasing. This is decreasing. It is positive but decreasing. And then from 0 to minus 1, that means from angle 90 degrees to 80 degrees, cosine theta is still decreasing. So the graph of cosine theta looks something like this. That's how the graph of cosine theta looks like. So now that I know the graph of cosine function, behavior of cosine function, I can see how this term behaves, and let me try to guess how the sign of the derivative looks like. At zero, derivative is minus 1. Because at 0 cosine theta is 1. So derivative is 1 minus 2 is negative 1. At pi by 2, cosine theta is 0. Sorry, derivative is 0. Here derivative is 0. Here the derivative is 0. At 2 pi, again derivative is negative 1. So what happened here is in the first interval, derivative is minus 1 and change to 0. So it moved from minus 1 to 0. So derivative is increasing from minus 1 to 0. Right? So it is right here, derivative is negative. Then in between pi by 3 and pi by 2, let me look at the derivative at 90 degrees. At 90, cosine theta is positive. Sorry, at 90, cosine theta is 0. So derivative is 1. Somewhere here, derivative is 1. In the first quadrant, all angles are positive. All three functions are positive. Then in the second quadrant, only sine is positive. Here only tan is positive. Here only cosine is positive. So you see, during the second and third quadrant, cosine theta is negative. If this is negative, altogether the derivative must be positive. So derivative, so it is 0 right over here, then it is positive and increase to some point and it decrease to 0. So in between derivative is positive. Then after pi by 3, derivative is now 0 and decrease to minus 1. That means it takes negative values. So sign of the derivative, sign change is from minus to plus to minus. And at these 2 points, we have horizontal tangent lines. Tangent line, so the derivative negative means function is decreasing and then it has a horizontal tangent line at here. This is a minimum point. Right over here, tangent, right before this point, tangent line is increasing. Derivative is positive. Slope of the tangent line is positive. Then zero will function decrease. Something like this. So this is a we don't know it is a absolute max minimum or a local minimum. So this is then relative minima. So local minimas are the absolute maximas and absolute minimas are by definition local maximas and minima. So it is not wrong to say this is a local minimum. This is a local maximum. And before this point, derivative is decreasing. So derivative is kind of decreasing. So this point must be at 2 pi, we must have a local minimum. And again, at this point, derivative seems looks like this. So this must be a local maximum. Right? Let me show you the graph of this function. I drew it using this software. Uh, so we found the nature of these critical points. We have this zero derivative at two different points. At pi by 3, you can see right over here, and at 5 pi by 3, it is a local maximum. Then at 2 pi, we have a local minimum, and at 0, we have a local maximum. So this example is not a simple one, it is a quite difficult one, but the point is, just by looking at the derivative, we can tell all about the function. You should try to try to redo this work after the class. Please go through this example and uh, try to recreate the solution by yourself, because this is quite important. Yeah. This problem is not easy. At the same time, it is not that difficult too. It combines few different topics that we talked about. Trigonometric behavior of trigonometric functions, then derivatives. So all together, when you combine all these things together, graph of the function looks something like this. That is exactly what we saw from the software. Right over here, x coordinate is 5 by 3. Over here, x coordinate is 5 pi by 3. This is where the x coordinate is 0 to 5. We also computed the y coordinates. At 0, y coordinate is 0. At this point, y coordinate is something like pi by 3 minus square root 2. At the topmost point, y coordinate is 5 pi by 3 plus square root 3. Over here it was 2 pi. 2 pi. We have all the x and y coordinates. We know how the function behaves. Between 0 and pi by 3, function is decreasing. That's why it has a negative derivative. Then from that point to the other critical point, 5 pi by 3, function is increasing. In my notes, I don't have that much information. I used a calculator to compute these numbers. But you see, I sort of get the absolute maximum and absolute minimum from these function values, calculator values. Um, let's look at one more example, and then will be our last example for today, last topic for today. I'm not doing well, so I don't think uh, I can continue for longer. Okay, so find critical numbers on the interval -2 to 2 for this graph. So -2 to 2, this is the function, or this is the derivative. Uh, I don't want to give you the function, but let's see. Let's say this is the derivative. Huh? Let's say this is the derivative. Uh, if this is the derivative, I can simplify it to get this solution, this equation. That equation has two features. At 1, derivative is 0, but we have a problem at 0 because 0 is making a 0 denominator. So x equals 0 is a bad point. Bad in the sense that the derivative does not exist. So derivative does not exist mean it is a critical point. So we have two critical points, x equals 1 and x equals 0. Um, Let me analyze this derivative. Let me analyze this derivative. So this is our derivative. The given function is, so critical points are x equals 0 and x equals 1. Now, I can plot those critical points and see how the derivative behaves. Let me take a number between -2 and 0. For a number between -2 and 0, it is a negative number. So third root is a negative number. This is negative. And numerator is positive because 1 minus a negative number. So with 2 minus signs, I get a positive number. But since I have a negative number in the denominator, derivative is negative. But I'm taking the sign of the derivative. Then from 0 to 1. 0 to 1, I can think about 1 half. So 1 minus 1 half is a positive number. Cubic root of a positive number is positive. So altogether this term is positive. The only problem is at 0, I have an undefined derivative. I know before 0 derivative is negative, after 0 derivative is positive. But 0 is a very uh, different critical point. That is not a, for there we won't have horizontal tangents. We will have a problem. Let's see what happens after between 1 and 2. After 1, I can take 1.5. 1 minus 1.5 is a negative number, negative 0.5, divided by cubic root of a positive number, which is positive. So that will be negative. So let me see what happens near 1. At 1 function graph is horizontal. Before 1, derivative is positive. That means function was increasing. And after 1, derivative is decreasing. So derivative is negative, that means function is decreasing. So the behavior should look something like this. At before 0, derivative is negative, function is decreasing. And after 2, after 0, function is increasing. I guess it should look something like this. Decreasing, then undefined points of the derivative, then increasing. So even though the derivative is undefined, this looks like a local minimum for the function. So that is how I analyze the sign of the derivative and critical points to get an idea about the behavior of the function. So at 0, I have a minimum. If I compute the function value, For some reason, I think there's a missing side. Uh, Let me find this function. Uh, it says the function should be 5 minus 2x, 5 minus 2x times x to the power 2 thirds. Let me compute the derivative and verify this is in fact the solution. So here I'll use the product rule. Derivative of 5 minus 2x is minus 2. When I simplify this, I get 10 divided by 3x to the minus 1/3 plus 4 divided by 3 x to the power 2 divided by 3 minus 2 x to the power 2 divided by 3. Oh, this is a minus. So 10x to the 1/3 by 3 minus 10 by 3x to the 2/3. It's minus mm, 1 minus x divided by x to 1/3. Yeah, this is our function. This is our function. Function is 5 minus 2x x to the 2/3 from minus 2 to plus 2. We found critical points. At minus 2, you can substitute minus 2 and compute the function value. At 0, function value is 0. At 1, function value is 3. Uh, Again, at 2, you should substitute 2 and compute the function value. And in that way, you can find the absolute maximum and absolute minimum. Let me leave that part for you. So this is our function, and we computed the derivative and verified it coincides with the given derivative. In fact, once we are given the derivative, finding the initial function is quite interesting. It has some applications. It is a useful operation. Differentiation tells you how to go from the function to its derivative. There is an operation similar to differentiation, which tells us how to go from the derivative to the function. Right? Uh, right. That is all for today. We'll meet again tomorrow, and in the meantime, I will update the our LMS page. Hmm? Um, do you have any questions? Uh-oh. So you could not see the. If something like that happened, you should unmute and tell me. I did not see your comments. Uh, let me show you. Yeah, this is the function. Now you should be able to see. Anyway, I will save this and send it to you. Hmm? We will have a mid exam near the end of the course. I cannot tell you the exact date, but it will be somewhere end of this month. Hmm? It is an online exam. Uh, I will post some problems and ask you to submit solutions to the LMS. Right? I will save this PDF and send it to you. Hmm? All right. Um, Mid exam will be near the end of this month. Hmm? Near the end of this month. In December, they will, by the December, before the December, I will finish this course. From December, they will start uh, this in computer course for you. Right? There are no more questions. I'll end the session. Have a nice day.